Okay, determine the slope of the curve f of x equals x squared minus 4x plus 3 at the point A and f of A. So this is I guess the next step in difficulty in our intro to calculus. We're not given an exact point of tangency anymore. We're just given any point that's on our curve. So if we do our secant slope and then of course use our limits, we can convert our secant slope to a tangent slope, and then we'll have an expression, and that expression will be in terms of A, and A is of course just an x value since that's the location in the ordered pair. And that expression will enable us to find the tangent slope anywhere on this curve. So of course that should make a lot of sense. There's a lot of algebra and toil, I guess, to get our tangent slope, and to just do that for a single point when we can do just a little bit extra work to have an expression that can give us our tangent slope at any point. So let's look to see how we can do this. So A and f of A, that's the given point. Even though there's no exact x value identified, we can still think of this as x1 and y1. And our second order pair is of course going to be a nearby, something close to A, h away. That'll be our second x value, and then the bit of algebra that's required is going to input that a plus h into our function f. And this will be our second set of coordinates, second ordered pair. And keep in mind, we're just going to form our secant slope, just rise over run. So once we can get some expressions for our y1 and y2, it's this simple slope formula, and then we just proceed and carry on with some limits. So we get a little bit of extra work to do. F of A, usually of course we know our x value, we know our y value of our point of tangency, but just keep in mind, figure out what f of A is, and that's inputting A into our function. So if I replace x with A, I replace x with A in my expression of course as well. And all we're really doing is converting our original function in terms of x, it's now in terms of A. So there's our first y value. So I'll just label that. Okay, so really nothing there, just switching the variable in that expression or in that function. Okay, now for the one that requires a little bit more work, for our second y value, we're going to have to figure out what f of A plus h is. So here's where we have to input a plus h into our entire quadratic function. So we have to square a plus h. We have to go minus 4 times a plus h, and then add 3, of course. So we have to square a binomial. So a squared, we're going to have 2 ah's. I think I'll just alphabetize that, but that makes no difference, obviously. And then we'll have an h squared, and then we'll distribute the minus 4. We'll go minus 4a, minus 4h, and then finally plus 3. So we can sort that, I guess, if we want. It makes no difference because we're going to have to subtract these two expressions in a few more seconds, but maybe we'll put the h stuff first. So typically what we would do, now notice we would typically only have one variable here. We would only have h, so of course it would make sense to start listing our h's off in descending degree. So we have an h squared, and I got a couple of terms with just an h to the power 1 in it. So I'll go 2ah minus 4h, and then I'll collect all the other stuff to the end, and we get a squared minus 4a plus 3. That should sound familiar. That, of course, is f of A. So when we subtract our orange expression here, f of A plus h, and we subtract f of A from that, a squared minus 4a and plus 3 are going to cancel. And maybe I'll just put brackets on that towards the end, so you can see that that actually is just f of A. So we're going to be left with 3 terms. Once we do our subtraction, we'll have 3 terms, all in terms of h in our numerator for our rise, and then of course we'll be dividing by h again because that will be our run, the difference between our two x values. So let's set up our secant slope. We'll keep those expressions handy, especially that orange one. So we'll say the slope of our secant is going to be y2. I guess I can write this out again. Hopefully is unnecessary at this point. But we're just subtracting our 2 y's and our 2 x's. I'll try to color code this. So our second y value, of course, is that 6-term beast in front of us there. So h squared plus 2ah minus 4h, and then plus a squared minus 4a plus 3. And we got a lot of stuff to subtract there, so we'll go straight across with that. And then I guess on the bottom, we have an a plus h. Remember, this is not necessary. We know we should have h on the bottom, but just in case you've forgotten. Okay, so now we're going to subtract our first x and our first y. And I'm sure you remember what it is, but we'll go up in a sec. The blue stuff up here. Our first x1 is just a, and our first y1 is just the expression a squared minus 4a plus 3 in light blue. So we'll subtract a, and notice we'll get h on the bottom, and then I have to subtract a squared minus 4a plus 3. And we better use brackets on that if we want to do that correctly. Of course, we have to switch the signs on all three terms. And hopefully you see what's happening here. We're going to get a squared minus a squared. We're going to get minus 4a. That'll be a plus 4a once we subtract it. And then we'll get 3 minus 3. So all that stuff is gone. And we have our secant slope simplified in one step. And now we are ready for the calculus moment, which is move these points infinitely close together. So before we deal with that, let's just rewrite this one last time. We'll have h squared plus 2ah minus 4h all over just in h. I guess I can cross off those a's. I'm pretty sure you recognize that a minus a is 0 on the bottom. And remember, this is our rise over run for our secant slope. Which color? Green. So this is rise over run for our secant. So now we move those 2 points infinitely close together via the magic of limits, and we will have our tangent slope. And keep in mind, it will be in terms of a, and of course I'll show you what we can do with this expression in a few more minutes, but it's pretty flexible. We can find our tangent slope virtually anywhere, as long as, of course, it's at an x value that our function is defined at, and a quadratic is defined anywhere, so that shouldn't be an issue. So let's wrap up. We'll say the slope of our tangent is going to be equal to the limit as the distance between these 2 points goes to 0. And I'm not going to write the slope of the secant anymore. This is what, example number 4 thereabouts. I'm sure we can just put our expression in here at this point, because of course this expression represents our secant slope at any value x equals a. And if we substitute h equals 0, or what I should say, if we let h approach 0, then every single term in our numerator and denominator will go to 0, and we get indeterminate form 0 over 0, which is hopefully hardly surprising at this point. So we have to do a little bit of algebra, which is not too intense when we're working with polynomials. We we factor out an h from the top, and we'll get h to the power of 1 plus 2a minus 4. And then in the bottom, we have another h, and then of course we can divide those h's, and there goes our 0 over 0 indeterminate form. So now we can let the limit do its work, because now if h goes to 0, h is going to go to 0, 2a is going to stay at 2a, and minus 4 is going to stay at minus 4. So the only thing disappearing there, of course, is just this little h in our numerator, because that's the only thing that's going to go to 0 that's affected by h. So we have an expression that is the slope of our tangent, and it's going to be 2a minus 4. So let's be hopefully super clear. The point of tangency was a and f of a. And f of a becomes kind of unimportant in terms of finding your tangent slope, as long as we just recognize what or I guess pick an x value that we want to find the tangent slope in. this is our x value, right? Our input, our original function. And we just have to input that into our tangent slope expression. So let's do a couple of those to make sure we're clear. If we have our expression here, maybe we can box that. So let's say tangent slope at x equals 0. Then I would say the slope of my tangent is going to be 2 times that x value of 0 minus 4. So our tangent slope is minus 4 when x equals 0. Maybe we want x equals 1. I'm just picking some random x values here. Then my slope of my tangent now is going to be 2 times 1 minus 4, which is 2 minus 4, or negative 2. And hopefully you can see that, yeah, that is quite powerful, because now we can get a tangent slope without having to do any algebra or limits. Our expression is sitting there, and all we got to do is input it. Our x values, which remember kind of just switches to an a value, but you can still think of it as an x value. And maybe we'll do 2 more, because this is an important one in terms of this quadratic function. At first it might seem a little strange, but we'll have 2 minus 2. If we input x equals 2 into our tangent slope expression, we'll get 0. And that means we have a slope that's equal to 0. That's a horizontal tangent line, and we'll see why that's an important point in one more second when we go have a look at Desmos. And one more x value. I think you probably have the idea at this point, but let's try x equals 3. Our slope of our tangent is going to be 2 times 3 minus 4, which is 2. So let's go check with Desmos, or use your TI Nspire, whichever you prefer. I'm going to use Desmos. And we'll input those 4 x values, and we'll just see that, yeah, our tangent slopes are minus 4, minus 2, 0, and 2. Okay, here we are at Desmos. There's our quadratic, and I have our tangent line stuck and graphed on there. And notice we have an expression here, 2a minus 4, which of course was our tangent slope expression. So right now when my slider is on a equals 0, we can see that the 2a minus 4 is outputting minus 4, and there's our tangent slope. And if you count the rise over run, looks like we're going 1, 2, 3, 4 down and 1 over to get to the next point on our grid there on that tangent slope, on that tangent line. So a tangent slope of minus 4 seems to be fitting the bill there. And then if we go to a equals anything here, but 1 was the next one we calculated. And we can see our expression is outputting negative 2. And we can also, if we look at our tangent's line slope, we can see that it looks like it's going down 2 and over 1. And then the other couple that we did x equals 2. There was the special one. If I can get it to stick, so we can see that actually identified the vertex, the minimum value of our function, because our tangent slope went completely horizontal. That's actually a way you can find all of your minimums and maximums on any function. If you can find a horizontal tangent, that's a pretty useful piece of information if you know where that horizontal tangent line actually occurs. But we'll worry about that more later. Let's finish off our last one that we calculated. So when a equals 3, our expression is outputting 2, and if you look at the rise and run of that tangent line, you can see that going over 1 and up 2, or I should say up 2 and over 1, is definitely the slope of that line. So our expression works, and it gives us a little bit more flexibility. Once we do our algebra, we've invested enough time in getting an expression that is able to find tangent slope anywhere in that curve, and that's a pretty good investment of our time, as opposed to just getting a single tangent slope for 10 or 15 minutes worth of work.